Hello, my name is Andrew, and this is my video lab for Physics 2211. This lab examines the motion of a fallen object. In this lab, I dropped a dry erase eraser from rest and analyzed its motion. The system was the dry erase eraser, and the surroundings were my hand, the air, and the earth. The purpose was to show how the gravitational force and the drag force act on an object dropped from rest. It was also to compare the predicted motion to the observed motion, and to construct a computational model that accounts for drag force and one that ignores it. The initial conditions of this lab are that the object starts at the origin. However, the height is 2.23 meters. This is because I centered the axis to where the object starts. The object starts from rest, which is initial velocity equals 0. The time starts when the object begins falling, at time equals 0. The mass is 0.0539 kilograms, which can be determined because the dry eraser weighs 1.9 ounces, which can be converted to grams and then further converted to kilograms. The formulas that I use include the gravitational force on the Earth's surface, which is force equals negative mg. I also use the velocity update formula, position update formula, and the drag force formula. The drag force formula is drag force equals negative 1 times the proportionality constant times the magnitude of the instantaneous velocity squared times v hat. It should be noted that since the ball is traveling straight downwards, v hat is negative 1, which makes the drag force equation for this problem simply drag force equals the proportionality constant times the magnitude of the instantaneous velocity squared. We can see from these free body diagrams that before an object reaches terminal velocity, the gravitational force is greater than the drag force. This causes the object to accelerate downwards since the gravitational force is greater. After an object has reached terminal velocity, drag force is equal to the gravitational force, and the object travels at a constant velocity, since the net force is equal to 0. This video was shot in slow motion in order to get more frames per second. The calibration stick is the height from which it was dropped, which is 2.23 meters. However, the displacement from the first point to the last point is negative 2.08, which is the displacement I use in the code later on. Later, I set the origin of the axis to where I was holding the dry eraser at the start of this clip. Using the tracker software, I obtained this data. The downward slope is due to the gravitational force. It begins to even out rather than continually become more steep due to the drag force acting upward on it. This is the code that I used to make the computational model with drag force. I set the initial position and velocity equal to the 0 vectors because the object is dropped from the origin. I determined delta t by dividing the total time passed by the number of observed points in the tracker, which resulted in 0.389 seconds. The proportionality constant b was determined by trial and error until the final position, negative 2.08, occurred at the time 0.7 seconds. This process gave me a value of 0.018 for b. I used the formula for gravitational force, which is F equals negative mg, in the code here, and I used the drag force formula here. F net is just the sum of these two forces. I used the velocity update formula here and the update position formula here. The computational model without the drag force is mostly the same as the other model, except the proportionality constant is 0, since this model doesn't account for drag force. Since there's no drag force, only gravitational force, or weight, is accounted for. This graph shows the two models, one with drag, one without drag, and the observed path of the ball. The model without drag continued steepening downwards because there is no upward drag acting on it. The model that accounted for drag was very similar to the observed motion, which shows the object approaches a constant terminal velocity due to drag force. How does drag affect the model? When drag force is ignored, the object is predicted to continually increase its velocity. When drag force is accounted for, the object reaches terminal velocity at which the velocity remains constant. This is shown in the computational model that includes the effects of gravity and drag force. When the drag force is equal to the gravitational force, it means that F net is equal to 0. If the object was thrown down, the terminal velocity would be the same because the drag force would be greater than the gravitational force until the two forces reach equilibrium at the same terminal velocity as if it were initially dropped from rest. If we look at these two graphs, we can see how the computational models show this. On the left side, the object started from the 0 vector for its position and velocity. However, it reaches negative 5.5 meters per second as its terminal velocity. On the right side, it starts with negative 10 as its velocity. However, it also ends up with a negative 5.5 as its terminal velocity. There are some sources of error in this lab, however. The camera angle may have made the tracker record the drop height as slightly lesser than the value it actually is, which may have led to some inaccuracies in the position time graph. Manually determining the center of the object at each time interval also slightly affects the values of the position time graph, since I cannot perfectly click the center of mass at each point. Thank you for watching my presentation.